Dr. Habibuddin Shaik, Department of Physics. Today we are going to discuss about semiconductors. In this lecture we are going to discuss few topics like introduction to semiconductors, then I will give you some basics about semiconductors, then the classification of materials, classification of semiconductors. Finally, I will end up this lecture by giving how the carrier concentration varies with the temperature. These slides give you a detailed explanation about where and all the semiconductors are being used, starting from healthcare industry, then automobile industry, aerospace industry, where not, everywhere the semiconductors are being used. It's not enough. You can see this slide where you can see the lasers, semiconductor lasers, and you can see solar cells, and you can see memory devices, and if you take your cell phones or CPUs, everywhere there is semiconductor. Okay. The processors that we use in our CPUs and smartphones, they are all made up of semiconductor. Before going to dwelling into the semiconductors, I will start with a very basic concept called Ohm's law. Okay, let's take a small conductor of length L and area of cross section A, and we apply a voltage to that. Now what happens when we apply voltage to a conductor? There will be a current flow through the conductor. Okay. Now the current which is flowing through this conductor is directly proportional to the voltage that we apply onto this conductor. Okay. Now as we increase the voltage, then the current will also rise. So the voltage is directly proportional to current. V is directly proportional to I. Now if we replace this, if we remove this proportionality, then we have to introduce a proportionality constant called R. Okay. This R is called the resistance of this conductor. Okay. Now if we rearrange the terms, then R is equal to V by I. Okay. This resistance R is defined as the ratio of the voltage applied to the current passed through the conductor. Now this resistance, the resistance of this conductor is directly proportional to the length of this conductor. Means as you increase the length of this conductor, then the resistance will increase, and this resistance is inversely proportional to the area of cross section of this conductor. Means as we increase the area of cross section of this conductor, then the resistance will come down. So the resistance is directly proportional to L and inversely proportional to the area of cross section. Okay. So R is proportional to L by A. Now if the resistance R is directly proportional to L by A, now if we remove this proportionality, then we have to introduce a proportionality constant called rho. R is equal to rho L by A. Now this rho is called the resistivity of the material or the resistivity of this conductor, which is given by rho is equal to RA by L. Let's see what is electrical conductivity. Like we have just learned about resistivity. Now let's see what is conductivity. Now the electrical conductivity of a conductor or material is the reciprocal of the resistivity. Okay. So sigma is equal to 1 by rho. Okay. So rho value is RA by L. So 1 by rho is L by RA. Okay. So the sigma is denoted as, the electrical conductivity is denoted as sigma, which is the reciprocal of the resistivity. Now this is the parameter which is used to classify the materials electrically in 3 different regions. Okay. Whether it can be electrical conductivity or it can be a resistivity. Okay, both are inverse reciprocal to each other. Now based on the conductivity, electrical conductivity of the materials has been classified into 3 different classes. One is conductor, the other one is semiconductor, and the third one is insulator. Now the conductors are those materials which allows the flow of current, whereas the insulator are those materials which does not allow the flow of current, whereas the semiconductors are those class of materials which allows the flow of current, not as good as conductors and not as bad as insulators. Okay. Now if you look at this beautiful diagram which tells everything about the classification of these materials. Now if you see the conductors, the conductivity of these conductors should be between 1 and 10 power 6. If the conductivity lies between this region, within this region, then those class of materials are called conductors. Now coming to the insulators, if the conductivity lies between 10 power minus 15 to 10 power minus 6, which is very low value, if the conductivity is such low, then those class of materials are called as insulators. Now come to this semiconductors. So those materials are called, these materials, the semiconductors are those materials whose conductivity lies between the insulators and conductors. Now if we see the scale, the conductivity should come in between 10 power minus 6 to 1. Okay. So those materials are called semiconductors. Now we are talking about conductivity and resistivity and all that. Now conductivity, where from this conductivity has come? Conductivity means what? How good the material conducts electricity. Conducting what? Conducting electricity. Electricity means what? Flow of electrons. Now the electrons has to flow in the material. So if the electrons are flowing very good, if the flow of electrons is very good in the material, then those materials are called conductors, are very good conductors. Now these electrons will be in the atom in the outermost orbit, valence orbit. Okay. So all the atoms, all the electrons which are in the outermost orbit are contributing to the conductivity. Okay. Now by somehow if we allow those valence electrons to flow, to conduct, to move in the material, then those materials are said to be conductors. Okay. If it is very difficult to move those electrons in some particular material, then those materials are called insulators. Okay. So this is how we have to understand the conductivity. If it is very difficult to move the electrons inside the material, those materials are called insulators, and if it is very easy to move an electron inside any material, then those materials are called conductors. Okay. Now as I said, the electrons are in the valence orbits, and we have to make the electrons to move from the valence orbit, and they have to pass into the conductor. Now how the electrons can pass into the conductor? Somebody has to give some energy so that the electron will come out of the atom and move into the conductor, right? So the energy we have to give, and the electron will flow into the conductor. Okay, how good or how easily electron is taking the energy to move into the conductor will be denoted in terms of band diagrams. Okay. Now if we talk about conductors, then we don't need to give much energy to a valence electron to move into the conductor, to flow, okay, to move into the material. So there is no gap, no energy gap here. Okay, the electrons will easily go from the valence band to the conduction. The red region is valence band and the blue region is conduction band. So there is no much energy required for an electron to move into the conduction band, though. So the electron can easily travel into the material. But see these insulators. In the insulator, as I said, the electrons need more energy. It's not very easy for an electron to move into the insulating material. So we need to give at least 5 electron volts, which is very huge energy, for an electron in an insulating material to go from a valence band to the conduction band. Okay. Now so these kind of materials are called insulators. Okay. So it is not very easy for insulators to conduct, because we have to give such a huge energy to send an electron from valence band to conduction band. Okay. See this semiconductors, the band, the gap, the energy difference between the valence band and the conduction band is lesser than the insulator, slightly greater than the conductor. Okay. So it is not so difficult for an electron to go from valence band to the conduction band. Okay. So these kind of materials where the band gap, energy difference between the conduction band and valence band, if it is lying between the insulator and a conductor, then those class of materials are called semiconducting materials. Now coming to a definition, let's define based on whatever we have learned so far. Let's define semiconductors. So semiconductors are those class of materials whose conductivity lies between insulator and metal. Okay. Now coming to the examples, what kind of semiconductors are there present in the periodic table? Silicon and germanium, they are pure and primary semiconductors that are available in the periodic table. Okay. In the similar way, there are some compound semiconductors like gallium arsenide, indium phosphate and all that. Let's discuss that a little later. But the primary semiconductors are silicon and germanium. Metals are aluminum, platinum, gold, iron, all these materials are called metals. And coming to insulators, rubber, then titanium oxide, aluminum oxide, all this kind of wood, all this kind of materials are called insulating materials. Means it is very difficult for an electron which is in the valence band of the insulating atoms to move into the material. Okay, it requires lot of energy. Now coming to the applications of these semiconductors, as I have already discussed in the previous slides, there is no place or no field in which semiconductors are not used. Okay, we are directly or indirectly completely depending on semiconducting devices. Okay, so there are so many sensors like light sensors, heat sensors, then proximity sensors, gas sensors, everything, everywhere we are dependent on semiconducting materials. Okay, how we are going so dependent on these semiconductors? Let's see. If we observe the periodic table, silicon and germanium, these are the only two primary semiconductors among all these elements. So these two are called primary semiconductors. These two semiconductors are belonging to the fourth group element. Okay, what do you mean by fourth group element? Fourth group element means in the valence orbit there are 4 electrons, which means when they form bond with any other atom, they contribute 4 electrons. Okay, that's how we define the fourth group element. Fifth group element means in the valence orbit there are 5 electrons. Third group means in the valence orbit there are 3 electrons. Okay. Now Coming to the classification of semiconductors, as how we have classified materials into three different categories like metals, semiconductors and insulators. Similarly, the semiconductors have also been classified into two different categories. One is intrinsic semiconductor, the other one is extrinsic semiconductor. So far what I have learnt, the purest form of semiconductor, silicon and germanium, they are called intrinsic semiconductors. Means intrinsic semiconductors are those semiconductors which are in the purest form. So the pure semiconductors are called intrinsic semiconductors. So silicon and germanium are the example. Now what makes the extrinsic semiconductor is, we take pure semiconductor, okay, by some means what we do, we introduce impurities into the semiconductor so that we get some advantage out of it. What is that advantage is the conductivity. We have already discussed that semiconductors are those materials whose conductivity lies between insulators and conductors, but still that conductivity is not sufficient or not enough to use them in different applications like sensors or whatever electronic components are there that we are using in the day-to-day life. Okay, so we have to increase the conductivity of these semiconductors or the pure semiconductors by some means. Okay, so the process of increasing conductivity by introducing some impurity atoms, some extra atoms or some foreign atoms into the host material or into the purest form of semiconductor is called doping. Okay, so by introducing the impurities into the semiconductor, we make them extrinsic semiconductor. Okay, so the purest form of semiconductor is called intrinsic semiconductor, and the doped form or the impure form of the semiconductor is called the extrinsic semiconductor. Let's discuss the purest form of semiconductor with the impurity atoms and what makes them, in what different kind of dopings we can do to the pure semiconductor. Let's discuss. Okay, let's first discuss about silicon. Okay, which is the purest form. Okay, the electronic configuration of silicon is 1s2, 2s2, 2p6, 3s2 and 3p2. Now you take the, if you take the valence orbit, you have 4 electrons in its valence orbit. Okay, which means silicon forms 4 bonds. Okay, let's start with a single silicon atom. Okay, if you take a single silicon atom, okay, silicon atom is having 4 electrons in its outermost orbit. Okay, that is for a single atom. Now if we take a bulk material or bulk silicon, okay, a block of silicon, then what happens? In a block there are thousands and thousands and lakhs of silicon atoms. Every silicon atom is bonded with the neighboring silicon atom. Okay, how it looks? It looks like this. Okay, so each silicon atom is bonded with neighboring 4 silicon atoms. How? Why it forms only 4 bonds? Because it has 4 electrons in its outermost orbit. So each silicon forms 4 bonds with the neighboring silicon atoms. Okay, all these ovals are bonds. Okay, now if we take this silicon, it is forming bond with 1, 2, 3, and if we extend the material, then it will form one more bond here. So every silicon atom is capable of forming 4 bonds with its neighboring atoms. So as we discussed, this is a pure semiconductor which is called intrinsic semiconductor. So in intrinsic semiconductor we don't have any impurities, all are silicon atoms, and this kind of semiconductors are called intrinsic semiconductors or I-type materials or I-type semiconductors. Okay, I means intrinsic. Okay, now let's see what happens to this silicon material if we change the temperatures. Now you go to the absolute zero, which is 0 degree Kelvin or minus 273 degrees centigrade, where you don't have any thermal energy. We don't have any energy at all. Thermal energy is kT. Okay, when you don't have T, that kT is equal to 0. You are not giving any external energy to this silicon crystal. When there is no energy given to the silicon crystal, see, are there any free electrons in this? There are no free electrons in this. Every silicon atom is bonded with the neighboring silicon atoms, 4 silicon atoms. So there are no free electrons in this. Now when there is no free electron in this in the material, then where from the conductivity will come? There will not be any conductivity. So at absolute zero, all the semiconductors will behave like insulators. Now let's see what happens if we raise the temperature of a semiconductor. Okay, let's discuss the situation at T greater than 0 Kelvin. Now slowly we are increasing the temperature from 0 degree Kelvin to slightly higher temperatures. Okay, let's come to room temperature, then 10 degree, 20 degree, 30, 40, 50 like that. Okay, so at some particular temperature what happens is the crystal will take that thermal energy. When it takes the thermal energy and the thermal energy is when it is sufficient to break this bond, then what happens? The bonds will break. Okay, now when one bond breaks, then one electron will come out of this bond. When one electron comes out of this silicon, when one electron is coming out of this silicon, you have one gap here, one hole here. So the complete material is having one electron which is left into the material plus one hole here. Okay, so when one bond breaks, there is one electron hole pair production. Now you slowly increase the temperature further, then what happens? Few more bonds will break, let us say 10 bonds have been broken. So you have, for each bond you have 1 electron and 1 hole. So if 10 bonds broken, then you have 10 electrons and 10 holes. 10 bonds have been broken, then you have n electrons and n holes. So for a pure semiconductor or an intrinsic semiconductors, when bonds break, then the number of electrons will be equal to number of holes. Okay. So at higher temperatures, the silicon will behave like a semiconductor. Okay. Whereas at 0 degree Kelvin, which is at absolute 0, the semiconductor behaves like an insulator. Okay, you have to remember this point. This is very important point. So let us see what exactly happens when you give energy to the silicon. Okay, let us give some energy to the silicon. Okay, this arrow is like some energy, some thermal energy. Okay, as soon as it take that thermal energy, what happens? I said bonds will break. Okay, then what happens? If one bond breaks, it gives 1 electron and 1 hole. Where do this electron will go? Electron goes into the material. Okay, so the electron is traveling in the material. When electron is traveling means what? It is conducting. Okay, when one bond breaks, the electron will be left into the material and it will be traveling. Okay, so charge is traveling means current is flowing. Okay, when current is flowing, it is conducting current. Okay, so the energy taken by electron will have some slightly higher energy than the energy when it is in the bond, when it is participating in the bond. So the higher energy electron will be staying in the conduction band. Okay, so when one bond breaks, then electron will go to the conduction band, leaving behind a hole in the valence. Like that, if some 10 bonds broken, then we have 10 electrons going into the conduction band, and we have 10 holes left behind the valence band. So the number of electrons will be equal to number of holes. Okay. Now for a silicon, okay, you have to give 1.1 electron volt corresponding temperature to give 1 electron to the conduction band. Okay, whereas for a germanium it is 0.8 electron volts. Okay, so that energy is represented as band gap. Okay, what do you mean by band gap? Band gap is the energy difference between conduction band and a valence band. Okay, the electrons which are participating in the bond, they are actually in the valence band. Okay. Now you are actually forcefully breaking those bonds and sending the electron to the conduction band. Okay, so how much energy you have to give? You are already in the valence band. You have to give slightly higher energy to break that bond, to send the electron to the conduction band. So that gap of energy, that energy difference is called band gap. Now let's see what is extrinsic semiconductor. So far we have discussed intrinsic semiconductors, which are purest form of semiconductor, which are also called as I-type semiconductors, and these semiconductors are behaving like insulator at absolute 0 temperature, and as we slowly increase the temperature, the thermal energy will be taken by the crystal or the material. A few bonds will break, and broken bonds will produce electron hole pairs, and the electrons will go to conduction band and participate in the conduction. Those type of materials are called intrinsic semiconductors. Now let's see what are extrinsic semiconductors. Now what are extrinsic semiconductors? We take a purest form of semiconductor, which is silicon or germanium, whatever it may be. Then we replace few of the silicon atoms by some foreign atoms. Let us take the pentavalent atom, which is phosphorus, okay, which is having 15 electrons in its outermost orbit. The electronic configuration which I have written here is for silicon. Now if I write electronic configuration of phosphorus, then what I have to write? I have to give one more electron here. I have to give, okay. If I write the electronic configuration of phosphorus, it looks like this. So from this you can see in the outermost orbit you have 5 electrons. Okay, which means phosphorus can form pi bonds with the neighboring atoms. But what we are doing, we are taking silicon crystal which is having 4 valence electrons, and we are replacing few silicon atoms with the phosphorus atoms. Okay, let's see what happens. We take a single crystal of silicon which is purest form, then we replace the center silicon atom with a phosphorus atom. Okay, observe these silicon atoms which are having 4 valence electrons, whereas phosphorus is having 5 electrons. Okay, now what happens with the silicon atoms? Phosphorus forms 4 different bonds with the neighbors, and it is left with one extra electron, that is this electron. It has formed 4 bonds with these 4 silicon atoms, but one electron is left here, which is the 5th electron, which is a valence electron of phosphorus, and which is loosely bound to the phosphorus. You have to remember this is very important. This electron belongs to phosphorus, which is loosely bound, but still it is bound to phosphorus, but it is loosely bound. Okay, let's discuss this. Now what happens to this? So this kind of semiconductors which are doped with impurity atoms like phosphorus, arsenic, so these kind of doped semiconductors are called extrinsic semiconductors. Now what happens, see here, we have doped it with the pentavalent impurity which is having 5 electrons in its outermost orbit. So 4 electrons have participated in forming bond with the silicon atom. There is one extra electron left here. Okay. Now this electron charge is minus, which is negative. So let's say we have doped pure silicon with the phosphorus. For every 100 silicon atoms, we have put one phosphorus atom. So effectively, there are 1:100 ratio of silicon to phosphorus atoms inside. That means for every phosphorus atom is producing one electron. So collectively, there are so many extra electrons residing in the material. Okay. So these kind of materials are called N-type materials or N-type semiconductors. Now what is this phosphorus doing here? This phosphorus is participating in the bond. It is forming bond with 4 different silicon atoms, plus it is actually donating one electron to the crystal or to the material, to the solid. Okay. So that's why we call this phosphorus atoms are called as donor atoms, okay, or donor impurities. So this is the story is same at absolute zero, how it behaves, and temperature greater than 0 Kelvin, how it behaves. Let's discuss. Okay. At absolute zero, which is T is equal to 0 Kelvin. As I said, there is no thermal energy, KT is equal to 0. So this extra electron, as I said, it is though loosely bound, it is still bound. Okay. There should be some energy given to this phosphorus this electron, so that it can come out of this phosphorus and it can participate in the conduction. But at absolute zero, there is no energy. So the electron will be attaching to this phosphorus atom only, so, and there are no free electrons inside. So the material behaves like an insulator. Though whether it can be intrinsic or extrinsic, the material behaves like insulator at absolute 0 Kelvin. Okay. So what happens at slightly higher temperature? Same story here. Okay. As the temperature is increasing, what happens? First, bonds will not break. The amount of energy required to break this bond is far higher than the amount of energy required to release this electron into the crystal. Remember this is a very important point. In intrinsic semiconductors, what happened? As we increase the temperature, at elevated temperatures, the bonds got broken. For every bond, we have one electron and one hole. Whereas in extrinsic semiconductors, before bond breaks, at very low temperatures itself, this 5th electron will come out of this phosphorus. The amount of energy required for this electron to come out from this phosphorus is very less compared to the amount of energy required to break this bond. Okay. So as we slowly increase the temperature, what happens? This loosely bound electrons will come out of that first. Okay. And they will participate in the conduction. Okay. Now when the electron leave the phosphorus, what happened to this phosphorus? If the phosphorus is having 5 electrons in its outermost orbit, then it is neutral. When an electron is leaving the phosphorus, then what happens to the phosphorus? Phosphorus will become phosphorus ion, positive ion. Okay. So when at slightly elevated temperatures, all these phosphorus atoms will behave like phosphorus ions. Okay. And these electrons which have come out of this phosphorus atom will be wandering in the crystal, and they make this crystal as N-type semiconductor or N-type crystal. So now see here. First, what happens? The extra electron will come out and it will be wandering into the crystal. Second, we are slowly increasing the temperature still. Now what happens? Slowly the temperature is so high that now the bonds will break now. Okay. Now we have electrons and holes, whereas previously we have only electrons. Okay. At slightly higher temperatures, only the electrons belonging to this phosphorus will be coming out and wandering into the crystal. There are no holes there. But now we are slowly increasing the temperature. So at higher temperatures, what happens? Now the bonds will start breaking and electron hole pairs will start creating. Okay. So effectively, number of electrons are more than the number of holes here. Okay. So in N-type semiconductors, we have number of electrons more than number of holes. Okay. Now see here. So what we have done to make N-type semiconductors? We have taken a pure silicon. Okay. We have taken an intrinsic silicon. Then we have doped it with phosphorus atom or pentavalent atom. Okay. Now see, in the pentavalent atom, what happened? At very low values of temperature, at very slightly low temperature itself, the 5th electron has come out. Okay. It has gone into the crystal and participating in the conduction. Electron is moving means what? Electron is conducting. So at very slightly low temperature itself, or for very low energy itself, the electron has come out and it is participating in the crystal. Okay. So if you have to represent it in the band diagram form, then it is not the electron which is in the valence band, it is going into the conduction band. This valence band and this conduction band are belonging to silicon, whereas this band is belonging to phosphorus. Okay. And the phosphorus atom is giving one electron. Now this phosphorus atom, okay, is giving electron to participate in the conduction for a very less energy. Okay. For very low temperatures itself, the electron is going into the conduction band. Okay. So this is the energy required for a phosphorus atom to give an electron to the conduction band is very less. Okay. So this this is very low energy compared to the band gap. So at very low energies, what is happening? Okay, now see, at very low energies itself, this phosphorus atom is giving that fifth electron to the conduction band. Okay, now keep on increasing the temperature and you reach at certain temperature where the silicon atoms, the bonds will break. Okay, that is very high temperature. Okay, that is this temperature. If you give such a high temperature, then the silicon atom is giving electron to the conduction band, but very low temperatures or at very low energies, what is happening? The loosely bound fifth electron is going into the conduction band, leaving behind this phosphorus ions. Okay, all these ions will become, all these phosphorus atoms will become phosphorus ions by giving the extra fifth electron to the conduction band. Okay, now the conduction band is having two types of electrons. One has come from the fifth electron from the valence band of phosphorus atom. The second type of electrons are the electrons which have come from the breakage of bonds from the silicon bonds. Okay, so these two type of electrons will be there in the conduction band, and these number of electrons will be more compared to the number of holes which are in the valence. Now let's discuss what is p-type semiconductor. It is similar to n-type semiconductor, but what we do here is we don't take fifth group element, we take third group element, which is trivalent element. It is boron. Okay, now if I have to write the electronic configuration of boron, up to here it is same, which is like, yeah, if I have to write the electronic configuration of boron, I can write up to here it is neon electronic configuration, plus 13 we should have. Okay, so 11, 12, then we have 13. So then the valence orbit of boron atom we have only 3 electrons. Okay, whereas in the silicon we have 4 electrons. As I said, if we have 4 electrons in the valence orbit, silicon can form 4 bonds. The orbit is having 3 electrons, then it forms only 3 bonds. Okay. Now what we do, we take a pure silicon, okay, and replace few silicon atoms with the boron atoms. Now we have taken a silicon crystal and we replace this center atom, silicon atom, by boron atom. Now you see, in boron atom, how many electrons we have? We have only 3 electrons. Okay, so these 3 electrons have formed bonds with the neighboring 3 silicon atoms. Now see here, there is no fourth electron here. There are only 3 electrons. So these 3 electrons have already formed bonds. This electron has already formed bond with this, and this one has formed bond with this, and this one has formed bond with this. Now you see, this electron is left for this silicon, and there is one gap here. That gap belongs to boron atom. Okay, like this, if we replace one silicon atom for every 100 silicon atoms with the boron atom, then there are so many gaps like this. Okay, so these gaps are called holes. Okay, now these gaps will behave like positive particles. Okay, that's why we call this material as a p-type semiconductor. Now see what we are doing here, we are doping a pure silicon with a boron atom. When we dope with the boron atom, what it is giving? Eventually it is giving a vacant space which is ready to accept one electron, okay, which is hunger of electron. Now it is ready to take electron means what? It is behaving like a positive particle. Okay, so these holes are behaving like a positive particle, so we call them as p-type silicon. Okay, now what they are doing, they are trying to accept an extra electron from the outside, from the host material or from the crystal or from the material. So they are trying to accept one electron. So these kind of dopants or impurities, we call it as acceptor impurity. Now again, the story is same for the behavior of this p-type semiconductors at T is equal to 0 Kelvin or T is greater than 0 Kelvin. What happens at T equal to 0 Kelvin? At T equal to 0 Kelvin, thermal energy is 0. So there is no supply of thermal energy to this p-type semiconductor, and there is no breakage of bond or there is no movement of charges. So this material behaves like an insulator, and at slightly higher temperatures what happens? This bond will break and electron hole pairs will produce, and it participates, and then they behave like a semiconductor. Not at all, they don't behave like insulator, they behave like a semiconductor. Okay. Now this kind of materials are having more holes than electrons. Okay, so that's why we denote it as number of holes greater than number of electrons. Okay. The same thing here. Okay, how we have denoted in terms of band diagram for p and n-type semiconductor, the story is same here. Okay, it's not for p-type semiconductors, it doesn't take much energy for a hole to be left in the valence band. Okay, so it is very close to the valence band. Okay, so this is called acceptor level, and the acceptor level lies very closer to the valence band. Okay, now let's see the carrier concentration variation with the intrinsic variation in the extrinsic semiconductors. Okay. Before discussing that, what is extrinsic semiconductor? Extrinsic semiconductors are doped semiconductors with the impurities. Okay. Take a pure semiconductor, then introduce impurities into the semiconductor. Okay. Now take a N-type semiconductor. What happens to the N-type semiconductor? We dope a pure silicon with a phosphorus atom which is having 5 electrons. Okay. So the 4 electrons have already participated in the bond and 5th electron is loosely bound. I told you to remember this point, that point we are using now. The 5th electron is loosely bound to the phosphorus atom. Okay. Now at very low temperatures, at T equal to 0 Kelvin, something like that, what happens? There is no energy supplied to the N-type semiconductor or N-type silicon. So the 5th electron also is bound to the phosphorus atom. There is no free electron moving in the crystal. So the material behaves like insulator. So there are no charges here. Okay, there are no electrons here. So number of charges are 0. Slowly increase the temperature. What happens? As we slowly increase the temperature, the amount of energy required to break the bond is more than the amount of energy utilized by the 5th electron to come out of the phosphorus atom. So which electron will come out faster? 5th electron will come out faster for a very low temperatures itself. As the temperature is slowly increasing, the 5th electron in the phosphorus atoms, they start coming out of the phosphorus and they will be moving into the crystal. Okay. So the number of electrons are slowly increasing. As we keep on increasing the temperature, what happens? As I told you already that 100 silicon atoms, we are replacing one with one phosphorus atom. Okay. Phosphorus atom for every 100 silicon atoms. Okay. Now this temperature, say all phosphorus atoms have given their 5th electron into the crystal. No, there is no phosphorus atom left with 5 electrons. Okay. So this temperature is such a temperature where all the 5th electrons of every phosphorus atom has gone into the crystal. Okay. So there is no extra phosphorus atom, or there is no phosphorus atom left in the crystal. So the number of electrons will be constant to some extent, to some temperature. Till here the electrons are increasing, the number of electrons are increasing, because as we increase the temperature, what is happening? The 5th electron is, all the 5th electrons are coming out. So the number of electrons are increasing slowly. Okay. Now when all the phosphorus atoms got ionized, means when all the phosphorus atoms have donated their 5th electron into the crystal, then there is no extra electron which can go into the crystal. So the number of electrons are constant, it is not increasing now. Okay. But you still keep on increasing the temperature. Okay. Now you reach to such a temperature, now the bonds will start breaking up. So apart from this constant electrons which were donated by the phosphorus atom, from this temperature the bonds will start breaking up. Okay. Now from here there will be an extra electron and hole. Till here only electrons. Okay. Only electrons here till here. Whereas from here the bonds will also start breaking up. Then you have electron hole pairs will be producing here. So the charge, the trace of the number of electrons will look like this. Okay. So this region is called ionization region. Okay. And this region is called extrinsic region, and this region is called intrinsic region. Okay. Why it is called ionization region? Because at absolute 0 all the electrons will be attached to their host atoms. As we slowly increase the temperature, what happens? First the 5th electron of phosphorus atom will come out. Okay. So slowly all the 5th electrons are coming out. So means phosphorus atom is getting ionized, it is getting ionized into positive ion. Okay. So that's why we call it as the ionization region. That's why we call it as ionization region. Okay. Now when all the phosphorus atoms got ionized, now how does it behave? The number of electrons will be constant here. There is no extra electron. All the electrons got donated to the crystal. Now though you increase the temperature, then there is no increase in the electron concentration. Okay. The phosphorus atom got depleted with the electrons. That's why we call it as extrinsic region or depletion region. Okay. Why we call it as depletion region? Because all the electrons of 5th electrons of all the phosphorus atom got depleted, means they have lost, the phosphorus atom has lost the 5th electron into the crystal. That's why we call it as a depletion region. Then at higher temperatures, what happens? The temperature is so high, or the energy is so high, that the bonds will also start breaking up. Then the electrons, to these electrons are also get adding up, and the number of electrons are rising. Okay. So this is how the number of electrons increases with the temperature in the extrinsic semiconductors. Okay. Now the third region is called intrinsic region, because what happens in intrinsic semiconductors? In intrinsic semiconductors, electron hole pairs will produce only because of breakage of bonds at higher temperatures. Okay. Now these electrons are increasing because of what? because of breakage of bonds. That's why we call it as intrinsic region. Okay, so the first region is ionization region because of ionization of phosphorus. The second region is depletion region or extrinsic region because of depletion of fifth electron from the phosphorus atom. And the third region is intrinsic region. Intrinsic region is because here the electrons are coming out because of the breakage of bonds, okay, like how it comes from the intrinsic semiconductors. Okay, that's why we call it as intrinsic region. Let's conclude whatever we have talked so far. We have classified the materials into three different classes: conductors, semiconductors and insulators based on the electrical conductivity. Now these semiconductors are again classified into two different classes, intrinsic and extrinsic. What are intrinsic semiconductors? Intrinsic semiconductors are the purest form of semiconductor. The basic semiconductors are the primary semiconductors available in the periodic table are silicon and germanium. And how the electron and holes produce in the intrinsic semiconductors? Because of as you raise the temperature, the bonds will break and the number of electrons will be equal to number of holes, because each bond broken will lead to one electron hole pair. N bonds broken means n electrons and n holes. Okay, number of electrons will be equal to n number of holes. The second class of semiconductors are extrinsic semiconductors. How extrinsic semiconductors will be produced? By doping it with the pentavalent impurity or a trivalent impurity. By doping it with pentavalent impurity, we get n-type semiconductors because of the fifth extra electron. By doping it with trivalent impurity, we get a p-type semiconductor because of the vacant space of one electron. Then donor level is close to conduction band in n-type semiconductor, and acceptor level is close to valence band in the p-type semiconductor. And we have also discussed how the number of electrons varies with the temperature in extrinsic semiconductor. It will be an ionization region because of ionization of phosphorus atom because of the fifth electron coming out of it and going into the crystal. Second region is extrinsic region or the depletion region. The third region is intrinsic region. Because of the breakage of bonds, the electron hole pairs will produce and the electrons concentration will increase. Thank you.